going to start talking about continuity. And in math, in calculus, when we talk about continuity, we normally think about, is this function continuous at a specific point, not throughout its life, right? So we just focus at a specific point. And there are three conditions that have to be met for something to be continuous at a certain point. It's not like an abstract word we throw around, right? It's a very concrete, specific thing. So for something to be continuous, it has to be, the function has to be approaching a unique y value, and f of that point has to equal that unique y value. All right? And so in calculus, this concept of approaching a value, not necessarily equaling a value, is very, very important. And we call that a limit, right? That's the concept of approaching a value without necessarily ever reaching it. So take a look at this graph right here. Suppose we are focused on this point C, right? And if you're on the x-axis, you can approach C from the left and from the right. So now suppose we are to the left of C, right here. This is you. And you're approaching C right here. If you're at the location of x1, where's the graph? It's right here above you, right? Now, if you move closer to C, does the graph move up or down? Down. And if you move closer towards like x2, the graph moves further down. And as you move closer and closer to C, the graph moves further and further down. And you say to yourself, oh my God, I bet you by the time I reach C, vertically, the graph will have reached a value of L. Does that make sense? Right? As you're approaching C, you're looking at this graph and you're like, oh my God, I bet you by the time I get to this, it will approach C. Okay, now suppose you're here, also approaching C. The graph is also above you. This time though, as you're walking towards C, is the graph still going down or is it going upwards this time? It's going upwards this time. And you're like, oh my God, I bet you by the time I approach C, this graph vertically will approach what value do you think? L. Also L, right? So because as you're approaching C from the left and from the right, vertically, the graph is approaching the same value, we say the limit of the graph as you approach C is L. Okay? Now, in this entire discussion, did we ever ask what is the value of C? What is the value of the graph at C? Did we ever ask that? No. Nor do we ever care, because the intent here is just to see where is the graph approaching vertically from the left and from the right. Okay? So, if from the left and the right, the graph is approaching the same vertical value, then we say the limit as x approaches C is L. And the way we write that is this, right here. Okay? So, the limit of f of x, that's how we read it, the limit of f of x as x approaches C is L. Okay, that's how we write it. Okay, So let's take a look here. And now we're going to look at the limits, not the values, just the limits. So for the first one, we're being asked the limit of f of x as x approaches -4. Okay, so -4 is here. As I approach -4 from the left, the y value is approaching what number? 3. As I approach from the right, the y value is approaching what number? 3. Because from the left and the right, the y value is approaching 3, I just say the limit is equal to 3. Okay. Now, let's go to 1. 1 is here. As I approach 1, what y value is the graph approaching? -1. From the other side, what y value is it approaching? -1. So the limit is -1. Okay. At 5, this is 5 right here. As I approach 5, as I approach 5 from the left-hand side, what y value is the graph approaching? 5, right here. What about from the right-hand side? What y value is it approaching? 2. Okay, 5 and 2 are not the same. Because they're not the same, I say the limit does not exist. You all missed it, Mean Girls people. Okay, so the limit does not exist. And we write it D-N-E, capital D, capital N, capital E. Now listen, no artistic creativity. Don't call it something else. Don't go with lowercase letters. This is how you see it. This is how you write it. That's it. Be artistic elsewhere, okay? Be creative elsewhere.
So if it's approaching different points from different sides, there's no limit?
The limit does not exist.
Okay. And then also for the second one,
yeah, I'm going to talk about that. I'm going to talk about that. Yeah. Okay. So now, as x approaches 0, let me clear some of this stuff. As x approaches 0, what y value are we approaching from the left side?
0.
What about from the right side?
0.
So the limit is 0. Okay, now, before you turn the page, don't turn the page. Now we're going to go and we're going to talk about, you know, what we were doing like yesterday and before, actual y values, right? So here, what is f of -4? What's f of -4? 3. What's f of 1?
It's undefined.
Undefined. There's an open circle there. F of 1 is undefined. What's f of 5? 2. F of 5 is 2 because of this, right? Yes. What's f of 0? 0. Okay. The point of this is the following. The moral of the story is this. The limit has literally nothing to do with the actual y value. Look at this point at x equals 1, okay? At x equals 1, there is no y value, but it has a very cute limit, right? Look at this one here. There is no limit, but it has a y value, right? So the two have nothing to do with each other. They are independent of each other. One is a limit where it's approaching from different sides. One is the actual y value. One other thing, this is DNE, does not exist. This is undefined. They're different things, okay? Because in the case of the undefined, it's not that the answer doesn't exist. It does, we just can't define it, right? There are different things, so don't interchange those, yeah.
How can you have like a limit of 0? Wouldn't that also, like if it's 0, then it's not?
No, that's just approaching 0. You can do that. Like, can somebody's grade approach 0? For sure, right? Can your bank account approach 0? For sure. 0 is a very approachable thing, right? Can, you know, how many chips you have left in a bag approach zero? For sure. Limit can definitely approach zero, right? Yeah. Yeah. Okay. All right. Okay, so let's move on.
Why is it called a limit if it just means like it's approaching? For another time.
It's the way that it was chosen.
This is the way.
So isn't an asymptote kind of a limit because the graph is approaching?
Look at that. Yes, it is. Yes, it is. In fact, that's the definition of an asymptote. It's a limit. We're going to get to that in chapter 2. Wow. Yay. Okay. Or maybe, actually, I take that back. We're going to get to it right now. Okay. Okay. So so this lesson is about continuity. But before we talk about what it means to be continuous, let's talk about what it means to not be continuous. Discontinuity. We've seen that word before. There are 3 types of discontinuity that we're going to talk about this year. One is an infinite discontinuity. Basically, this is where you have a vertical asymptote. Okay? So, this is your vertical asymptote. Okay. An infinite discontinuity is where there is a vertical asymptote because as x approaches c, do you see how from the left-hand side, the graph approaches negative infinity? From the right-hand side, the graph approaches positive infinity. Last time I checked, negative infinity and positive infinity were not the same number, so there is no limit there, so that's a discontinuity, right? What's one way you can get that, right? Like, so for example, if you have f of x is equal to x over x minus 3. Do you remember that? At x equals 3, there is a vertical asymptote, right? So that's one type of discontinuity. Another type of discontinuity is a jump discontinuity, clearly, okay? Another type of discontinuity is a removable discontinuity. Remember how we get removable discontinuity. This is if you have like f of x is equal to x minus 3 over x minus 3x plus, let me do this, x minus 3x plus 3 over x minus 3, right? So remember, the x minus 3's cancel, so at x equals 3, you have a removable discontinuity. Okay, so these are the 3 discontinuities, the 3 types of discontinuities. Okay, let's talk about the continuity test. All right, to say something is continuous at a point, it has to meet 3 conditions, right? It's literally, it's like number 1, pass, number 2, pass, number 3, pass, done, okay? Number 1 condition is for something to be continuous at x equals c, the first condition is f of c has to exist, all right? So for example, if you look at these, for which one does f of c exist? 1, 2, 1, 3, and 4, right? Okay. The next one is the limit has to exist, okay? So if you go over here, for which one does the limit exist over here? What numbers does the limit exist? 1, 2, and 4. Okay. The third one is, remember that value of f of c? And then remember that limit? They have to equal each other. So the limit has to equal f of c. So now let's go over here. For which one where the limit exists does the limit equal f of c? This one and this one, right? The limit is 0, f of c is 0. The limit is 3, f of c is 3. So those two are the points where the function is continuous. Okay? All right. So let's take a look at this one. Yeah.
So a function can be continuous
Take out your calculators.
at some points, but not other points?
Correct. A function could be, yeah. Absolutely.
So it can be both.
Yeah. That's why we never talk about a function being continuous. We say, is the function continuous at x equals 2?
Got it.
Yeah. Okay, go ahead and graph this. It's a, you know, your basic parabola. Go ahead and graph it. So to show if something is continuous, you literally have to say, okay, step 1. Okay, so now the question is f of x continuous at x equals 1? So step 1, you find f of 1. F of 1 is 1 plus 1 plus 1, 3. Right? You just plug it in. Okay, now you want to look at the graph and analyze it at x equals 1 to see if the limit approach, what's the limit, right? So let's see. What was it? It was x squared.
X squared plus x plus 1.
Okay, and here you're just going to kind of like visually inspect, right? You're just going to visually inspect. So here is x equals 1. So if we trace, all right, look at this. It's x equals 0.3 right now. Do you see how, like, as I approach 1, it looks like this is approaching 3, right? From this side. And then if I'm here, and if I approach 1 from this side, it looks like it's also approaching 3 from that side, right? So, okay, so I just did that. And so the limit of f of x as x approaches 1 is 3. So the first step is, does f of 1 exist? Yes. Does the limit as x approach 1 exist? Yes. The last one is, are these two continuous? So you say, since f of 1 is equal to the limit of f of x as x approaches 1, therefore f of x is continuous at x equals 1.
You have to have the capital M in the
What M?
The capital M, L.
It's actually not a capital. It doesn't matter. Okay?
Wait, how do you find, like, how did you know it was 3 again for the limit one?
I looked on the graph. As I was approaching x equals 1, the graph was going up to 3. As I was approaching x equals 1, the graph was going down to 3. Okay? All right.
F of x is continuous.
Yes. Okay, now let's do another one.
Wait, why is
Wait,
it
can
R
you
of
go back
x?
up for 1 second?
Huh?
Why is it R of x?
Where? It's not. It's f of x. It's f of x. My pen is being glitchy. They're f of x. Okay. Next one we're going to do is this. X plus 1 over x minus 2 at x equals 2. Okay, the minute you see this, why not? The denominator will be 0, so what is there?
No, discontinue the whole thing.
At x equals 2, there is a what?
Oh.
It's a vertical asymptote. It's an infinite discontinuity. Okay, fine. We all know this, right? But you have to justify it. Okay, it's not enough to know it. All right. So, okay. So the first step is f of 2. F of 2 is 2 over 0. No, 3 over 0. Which is undefined. So there we go. It already failed step 1. It's an all or nothing deal, right? So you say not continuous at x equals 2. Now, suppose I ask you, what type of discontinuity is this? What would you say? Infinite discontinuity at x equals 2. All right, take a look at this one. Yeah, this one's a removable discontinuity, right? Because, so f of x is equal to x minus 3, x plus 3, over x plus 3. These go away, okay? So f of negative 3 is 0 over 0 in this case, okay? So it is not continuous at x equals negative 3. This one is removable discontinuity.
F of negative 3 is negative 6 over...
Now if you put it over here, it's 0 over 0.
Oh.
Okay? Okay, now. Okay, so here we go. Determine and classify the discontinuities, if any. All right, so let's take a look at this one. So here I factor, right? Is this continuous? No, right? So what kind of discontinuities are there?
X equals 0 and x equals negative 3.
Absolutely. Okay, so there is a removable discontinuity at x equals 0. There is an infinite discontinuity at x equals negative 3. Okay, good. So these are infinite and removable. Okay, let's talk about jump discontinuities. For the first few, I've actually put in a grid here for us to graph because I want us to see a visual, but you should be able to do these without ever graphing them. Okay, so take a look at this one. So 2x squared, right? So hang on, give me 1 second here. Okay. Okay, so let's do the continuity rules, right? So what's rule number 1? You say f of 2. So in this case, we know if there is something, it's going to be at x equals 2, right? Because that's where. So what's f of 2 in this one? 3. Okay, next, we want to look at the limit, right? We want to look at the limit from the left, and we want to look at the limit from the right. Is that right? So when we have x equals 2, if I were to graph this, what would it look like? So at x equals 2, look at this function. What will the value be? 8. And it's an open circle, right? Right here. And so it basically looks like this. Right? Because it's a parabola. And then this next one is x plus 1. So at x equals 2, what does it look like? It's 3. And it's a closed circle. And it looks like this. Yes? Everybody okay with this? I don't know why I can't draw a straight line. Everybody okay with this? So clearly there is a jump discontinuity, right? Now, look at this. If you look at the graph, as you approach -2 from the left, where is the graph approaching? What number? 8. From the right, where is it going? 3. Okay, so here's how you write this without ever having to graph it. The limit of f of x as x approaches 2 from the left side. You know how you say left side? Minus, because it's from like the negative side, equals. And you literally plug in 2 into this function and you get 8. And then you say the limit of f of x as x approaches 2 from the positive side. Plug 2 in here and you get 3. Are those two numbers the same? No. So you say limit of f of x as x approaches 2 equals DNE. So number 3, limit of f of x as x approaches 2 does not equal f of 2, therefore not continuous at x equals 2. What kind of discontinuity is this? Jump discontinuity. Yeah. Okay, but not all piecewise functions will have discontinuities if they have them. Okay, so let's take a look at this one. Let's do this one without graphing first. So, what's f of 1? 3. Okay, limit of f of x as x approaches 1 from the negative side, that's 3, right? Limit of f of x as x approaches 1 from the positive side, how much is that? 3. Oh. So what's the limit? Limit of f of x as x approaches 1 is 3. So for the third step, you say limit of f of x as x approaches 3 equals, as x approaches 1, equals f of 1, therefore continuous at x equals 1. Okay? So look at this one. You get 3, 3, closed circle, it's continuous, right? And if you graph it, it's like this. Right? So this is continuous. Okay. All right. Take a look at this one. Number 1. What's f of 1? It's undefined because it's all open circles. Okay? But what if I asked you for the limit, right? Limit of f of x as x approaches 1, 3. Limit of f of x as x approaches 1 from the negative side and from the positive side. They're both 3. So the limit of f of x as x approaches 1 is actually 3. So does this have a limit? It does. It just doesn't equal, but f of c doesn't exist. So this is not continuous. So you can either say, you can actually say not continuous because f of c or f of 1 is undefined. Okay, what kind of discontinuity is this? It's a removable discontinuity. Right? So these two are the same equation, except instead of this, there's a tiny hole there. Yeah.
Which side's the negative side and which side's the positive?
The left side is the negative side, so it's like from the negative numbers.
So if you're going this way, it's
This-
negative. If you're going this way, it's positive.
No. Well, wait, I couldn't. Yeah. This is from the negative side,
Okay.
and then this is from the positive side.
So positive's going like the reverse way.
It's literally coming from the positive side.
Okay.
Yeah. Okay, so take a look at this one. Now I have to check for 2 points, right? At -1 and at 2. So let's see at -1. Okay, so what's f of -1? Oh, yeah. Okay. Limit of f of x as x approaches -1 from the minus side. -5, right? No, -1. Oh, is it? Okay. So limit of f of x as x approaches -1 from the positive side. Also -1. Yeah. Yeah.
Wait, where did you get -5 initially from?
I added wrong.
Okay.
Okay? Are we okay with this? So the limit of f of x as x approaches -1 is -1. So since f of -1 equals the limit of f of x as x approaches -1, therefore f of x is continuous at x equals -1. Now let's do x equals 2. What's f of 2? Yeah. What's the limit of f of x as x approaches -2 from the minus side?
-1.
Okay. Well, how about from the positive side? Also -1. Okay. So number 3, f of 2 equals to the limit of f of x as x approaches -2. So this is continuous.
Wouldn't it be +2, not negative?
Oh, +2. Why do I keep saying -2? Sorry, guys. Okay. Do we need to do another one, or are you guys okay? We're good? I think we're good. Okay. Let's talk about end behavior. Okay. Let's talk about end behavior. Okay. So end behavior, we know this from Algebra 2, right? The end behavior of a function describes how something behaves at either ends of the graph. And then, so last year in Algebra 2, I hate that notation. It's like as x approaches f of x. I hate that notation. Now it's just limit, right? So as x approaches infinity, f of x goes down to -infinity, right? So I just say the limit of f of x as x approaches infinity is -infinity. Yeah? And then here, it's like this. The limit of f of x as x approaches -infinity is +infinity. Okay? All right. So take a look here. Okay. Let's talk about end behavior. So for this one, the limit of f of x as x approaches +infinity, the limit of f of x as x approaches -infinity. So as x approaches +infinity, what y value is the graph approaching? 0. As x approaches negative infinity, what y value is y approaching? The 0. Okay, what about this one? Limit of f of x as x approaches infinity. Limit of f of x as x approaches negative infinity. Okay, as x approaches infinity, what y value are we approaching? Infinity. What about on the other end? Negative infinity. Yay! Right? Okay, we'll stop here. You can actually do the majority of the homework. I'll take a look if there are any that you can't do, and I'll email you guys. Okay?
What's the thing on that?